All right, let's jump right in. We're about to tackle something that, on the surface, sounds a little crazy. We're going to use something totally random, like rolling dice, to understand the super predictable world of chemical reactions. I know, it sounds like it shouldn't work at all, but you're going to see how the laws of chance can actually tell us a whole lot about the laws of chemistry. So that really is the big question, isn't it? Can a simple game, a bunch of dice in a box, really explain something as exact as chemistry? You know, how fast reactions go, how they find their perfect balance point. It feels like a long shot, but stick with me because this is a fascinating idea. There's really only one way to figure this out. We're just going to have to do it. Let's run the experiment. Simulate a reaction with a whole pile of dice and see if our little game actually lines up with reality. Okay, first up, we're going to look at reaction kinetics. And don't worry, that's just the fancy science way of saying how fast a reaction happens. We're starting simple, with a one-way street. Our starting materials, the reactants, are going to turn into a product. And that's it, no turning back. So, here are the rules for round one. We start with 165 dice, and they're all our reactants. We give them a good shake, and any die that lands with a 6 facing up has reacted. We just scoop those out and move them over to the product bin. Then we count what's left and we do it all over again. Simple as that.
And here's the cool part, the translation. Just imagine each of these little dice is a single molecule. And every time we roll the bin, 1 second of time has passed. So by just counting the dice after every single roll, what we're really doing is plotting concentration versus time. That's the heart of reaction kinetics right there.
So after we do this a bunch of times, we get our data, and it makes a curve. See, the reaction is really fast at the beginning, when there are tons of dice, but then it slows down as there are fewer and fewer left to react. So that leaves us with a puzzle. How in the world do you find a single reaction rate if the rate is changing every second? It's a classic chemistry problem. And chemists have a really clever trick for this. They've got this toolkit of equations called the integrated rate laws. And the whole point is to take our curved data and plug it into these different equations to see if we can magically turn that curve into a perfectly straight line. And if we can, bam! The slope of that straight line is our reaction rate, our constant K. And for our dice game, it just so happens that the first order equation is the one that works, giving us that beautiful straight line. Okay, now check this out. What if we change the rules to make it easier? In our second trial, a die reacts if it lands on a 5 or a 6. We've literally doubled the chances. And no surprise, the reaction is way faster. Well, this is a perfect model for something called activation energy in chemistry. Making the dice game easier is just like lowering the energy barrier that molecules have to cross to react. A lower barrier means a faster reaction. It just clicks. So we've got one-way reactions down. But, in the real world, chemistry is usually more complicated. Reactions are often a two-way street. Products can actually turn back into reactants. This is called a reversible reaction, and it leads us to one of the most important ideas in all of chemistry, equilibrium. Okay, so time for new rules. The forward reaction is still fast. Our reactants become products on a 5 or a 6. But now we're adding a twist, the reverse reaction. Any product dice that land on a 6 get to go back to being reactants. So we're going to roll both bins at the same time, move the dice back and forth, and see what happens. Right at the beginning, after just the first roll, it looks pretty much like you'd expect. We've got a giant pile of reactants and just a tiny little pile of new products. The forward reaction is totally in charge here. Fast forward to roll 10, and wow, things look different. A whole bunch of reactants have moved over to the product side. But look at that. As the product pile gets bigger, that reverse reaction starts to kick in. Some of those products are now making the journey back to being reactants with every single roll. And then this happens. After about 20 rolls, the numbers just stop changing. The piles level off. It's not because the dice stopped reacting, it's because the number of reactants turning into products is now perfectly balanced by the number of products turning back into reactants. The net change is 0. We've hit a stable state. This stable state, this balance point, it has a special name. It's a huge deal. What we've just found with our dice is chemical equilibrium. This right here is the aha moment, where all that random rolling and shaking settles into a predictable, steady balance. Now, the most important word to remember here is dynamic. This is a dynamic equilibrium. That means the reactions haven't stopped, not at all. Dice are still being rolled, molecules are still flying back and forth. It's just that the speed of the forward reaction is now exactly equal to the speed of the reverse reaction. It's a state of perfect, nonstop balance. So it's one thing to see this happen with our eyes, which is pretty cool. But here's the next question. Can we predict it? Can we use math based on the rules of our game to calculate exactly where that balance point should be before we even start rolling?
And the answer is, you bet we can. That balance point in any reaction can be described by one special number. It's called the equilibrium constant, or just K. And our little dice game has given us everything we need to figure it out.
Now this is where it gets really amazing. It turns out there are two totally different ways we can find this number, K. The first method is super straightforward. You just wait till you hit equilibrium, and then you divide the number of products dice by the number of reactant dice. Easy. The second method is more theoretical. You divide the rate constant of the forward reaction by the rate constant of the reverse reaction. So, should these two completely different paths lead to the same answer? Incredibly, they do. They match almost perfectly. This is the ultimate proof that our model works. It doesn't matter if we physically measure the final piles of dice or if we calculate it based on the reaction speeds, we end up at the same exact equilibrium constant. The game worked. The random rolls of the dice successfully predicted a fundamental law of chemistry. So let's just take a step back for a second and think about what we just figured out just by playing this simple game. We've built a powerful bridge between the chaos of a die roll and the concrete laws that govern the chemical world. So what are the big takeaways here? First, we saw that reaction speed is really just a game of probability, which is a fantastic way to think about activation energy. Second, we learned that equilibrium isn't some static, boring endpoint. It's a living, dynamic balance. Third, we proved that this balance point is totally predictable, all determined by the ratio of those forward and reverse speeds. And maybe the biggest idea of all? That sometimes a really simple statistical model like rolling dice can be an incredibly powerful way to understand a very complex system. The source material we've been exploring really says it best. The whole point of this isn't just to memorize facts, but to get a real, hands-on, intuitive feel for how all these invisible processes actually work. And I really hope you've gotten a little bit of that today. And that kind of leaves us with one last big thought to chew on. We used a simple game to model molecules, but this core idea, using simple rules and probability to make sense of complex behavior, that applies to just about everything. Economics, the spread of diseases, how information travels online. It really makes you wonder, doesn't it? What other huge secrets about our universe are just sitting there, waiting for us to come up with the right simple game to explain them?